It is going, the objective of Lab 2 is to attach an accelerometer, a 3-axis accelerometer to the 328P and also connect 6 LEDs which will indicate plus or minus acceleration in each of the 3 dimensions, 3 axes. And then we're going to use pulse width modulation to be able to control the brightness of each of those 6 LEDs. Make sense? We divide it into 3 parts. The first part is the accelerometer, right? Talking to the accelerometer and reporting back the data from the accelerometer on the UART. Part 2 is to connect the 6 LEDs and get those working. And then part 3 will be to combine them together. So you'll have the accelerometer, and as you apply forces to it in 3 dimensions, you'll see those forces indicated on the 6 LEDs. Does that make sense?
I should remember to upload. I'll try to upload that video to Blackboard. So I've had a video of it.
Oh, okay, yeah, that'd be good. Yeah, Charles has a video of it working, so you can get an idea of what we're expecting the end product to be. So 2 lectures ago, I covered SPI and how to use hardware master SPI on the 328. I also covered the control registers that you'll be accessing on the accelerometer. So starting with this week, you're going to have to go back and maybe review some of that material. It's in the slides and on the online lecture, and of course we'll have a handout as well. Then last week I covered how to do a software SPI master and then feed that back into the hardware SPI slave on the 328. I didn't have it fully working by the end of the lecture because I had a bug, actually 2 bugs, which I found right after the lecture and I posted on the announcements board. I also put an addendum on the YouTube video as well. Basically, there was a bit in the SPI control register called MSTR, master, and I was setting it to 1, which obviously should have been 0 because it wasn't the master. I was making a slave. And I think the other problem was the master in, slave out, I had marked in the DDR register as being an output when it should have been an input. So basically those 2 bits were what was causing the issue. So the corrected code is posted if you're interested in that. So today, I don't really have any new conceptual material to present. And the feedback I've gotten in the past semesters has shown that I think all of y'all prefer to have more technical demo-based lectures as opposed to doing concepts. So I'm going to go ahead and just do another demo, which hopefully will help you in lab. Keep in mind though that I can't give you a demo of exactly what you're doing in lab. So I'm trying to find things that are closely related enough that once you see how I work those out, then you should be able to adapt that to what's required in the lab project, right? So I mentioned pulse width modulation is a part of this next lab. I've talked about this a couple times briefly, but just to review, PWM is a way that you can create a quasi-analog signal on a digital pin. So you have a periodic signal, periodic in that it repeats, and then there's a duty cycle, which is the percentage of time that periodic signal is high or is asserted within each of the periods, and that will sort of be translated if you take with that pin, if you take that signal and you apply a low-pass filter to it, in other words, you're plugging it into something that really only recognizes lower frequencies, then it will see that as an analog signal as being whatever the duty cycle is multiplied by the voltage of the pin, which is Charles, 3.3 or 5 volts PWM pins?
It'll be whatever VCC is.
Yeah, so 5 volts. So if your duty cycle is 50%, meaning that the clock is high half the time and low half the time, and that repeats, then that will look like a 2.5 volt signal, 50% of 5 volts. if I view that pin as an entity that only understands low frequency signals. If you plug it into a speaker directly, it may sound a little noisy because the sharp transitions up and down create high frequency noise, right? But you can solve that. Like I mentioned, there's a whole class of audio amplifiers called Class D amplifiers, which are used in cars and type applications, and those are PWM, except they just have a built-in low-pass filter inside the amplifier that takes those high frequencies out. And those work essentially with this PWM. So it's kind of neat. It avoids the need for a full digital to analog converter on a chip, which is kind of tricky to make because whenever you have a mixed signal chip, you have digital and analog circuits on the same chip. The digital interferes with the analog, so makes it tricky to design. You have to isolate those circuits. So this is a way that we can do kind of a quick and dirty analog output signal. I also mentioned before briefly, I didn't go into a lot of detail, but I talked about these timer/counters, and I sometimes call them timers, sometimes I call them counters, and I'm sorry for the confusion. But there's these devices on the 328P called timer/counters, and there's 3 of them, and they're basically just counters. They're a register that counts, and they can be used for several different things. They can be used to count external events. They could be used to count cycles between 2 points of your code. They can, which we've used them for that before, right? They can be used to generate interrupts at predefined timing intervals, which we just used in the last lab. But the other thing you can use them for is to create PWM signals in hardware as opposed to having to do it in software. And what that means is that you basically tell them what sort of PWM signal you want to create, and they just go off and do it in the background while the processor is able to run software that does other things, as opposed to having to use software to set the output high, set the output low, set the output high, and so on. So the counters, so each one of these counters, so there's counter 0 through counter 2. Counter 1 is a 16-bit counter. Counter 0 and 2 are 8-bit, which is super confusing. I don't know why they just didn't make the first counter 16 bits. The control registers that you use to access these counters are also enumerated starting from 0. So you'll see 0, 1, and 2 in the names of these control registers as well, that referring to each of the 3 counters. But each one of these counters, if you look at the pinout, they have these outputs called OC2A, OC1B, OC1A, OC0A, OC0B, OC2B. So there are 6 outputs called OC and then 0, 1, or 2, referring to the 3 counters, and then A or B. So each one of the 3 counters has 2 of these OC outputs. I think OC stands for oscillator compare, I think. And those are used for the PWM signal. So basically what that means is that this chip supports up to 6 hardware PWMs because you can have 2 per counter peripheral. However, you have to keep in mind that these pins are all general purpose. So for example, OC0A is also the port D bit 6, as well as the analog input 0, because this chip actually does analog input, not output, but input, as well as one of the PC interrupt pins. So that means is that if you want to use one of these, it may interfere with something else you were planning on using that same pin for. Okay, you got to be aware of that. And I'll show you an example of that here in the demo. Okay, so last time I covered, I talked about this, I think there's 3 control registers for each one of these counters, A, B, and C. The first one, TCCR 0, and that 0 refers to counter 0, and A refers to the first of the 3 control registers for counter 0. There's a bunch of bits in here that you can set, and they're named here, and they're described in these tables. Then there's also B. There's TCCR1B. Actually, I was a little inconsistent here, wasn't I? Yeah, so there's a 0 here, 0A, and then I've got 1B, so I mixed, but all the control registers for each of the 3 counters are the same. It's just that, it depends on whether you have a 0, 1, or 2 here, and then the control registers themselves are enumerated A, B, C. Okay, so this one we've used. This one allows you to divide the clock, so you can have the counter activate on just the raw 16 megahertz clock, or you can have it a slower version of that clock divided by 2 all the way up to 1024. And so those are set with the low order 3 bits. Right? Okay, so I'll come back to that in a minute. I'll talk more details about that. Now let's talk about LEDs for just a minute. This is a slide, obviously, I got from my CSCE 190 talk. You guys might have seen this. LEDs are diodes. LED stands for light emitting diode. A diode is a semiconductor. Semiconductors semi-conduct electricity, but not really. They don't really conduct electricity by themselves. Semiconductors are crystals, like literally crystals. So you think of a conductor is like metal, right? But semiconductors are not metal. They're crystals. They're grown crystals. Silicon is actually, you think of it as basically sand, except sand is silicon dioxide, which is an insulator. Semiconductor silicon is pure silicon, and that's not something that you find naturally. That's why they're grown. But anyway, so how do you make a semiconductor conduct electricity? You add dopants to it, which serve as the charge carriers. They carry charge, they carry electricity. And so there's 2 types. There's p-type and n-type. P is positive, which means you put a dopant in there, a charge carrier that comes from an element from group 3 on the periodic table, meaning that it's missing an electron, so it has positive charge carriers. And n-type silicon is negative silicon. It's when you put a group 5 element in there that has an extra electron. So the lack of an electron, which some people call a hole, or an electron, those are the charge carriers. They make the silicon conductive. Charge carriers can also be seen like if I hold up 2 wires with a very large voltage potential and I start bringing them closer, you'll see eventually it'll arc. And that arc is actually when the charge, the voltage potential difference ionizes the air, which is an insulator between the two ends of the wire, and that ionized air becomes a plasma, which contains charge carriers, which is why it arcs, right? So it's the same kind of thing. Now, if you put a p-type and an n-type together, they become a diode. And so what happens is kind of this neat effect where if you have a positive voltage on the p-type side and a negative voltage potential on the n-type side, the charge carriers in the n-type get attracted to the junction between them, between the 2 sides. And that the fact that the charge carriers get attracted to one another makes this thing conductive, right? But if you put the reverse on, you put the positive charge on the N side and the negative charge on the P side, you get this reverse effect where the charge carriers actually get repulsed away from both sides of the diode. And so it actually cuts the connection there when that happens, so it doesn't conduct anything. You end up with nothing but silicon here in the middle, which doesn't conduct. So it kind of squeezes off the connection when you reverse. That's called reverse biasing. So what that means is that diodes only conduct electricity in one direction, which we are going to take advantage of that in this example. So I wanted to come up with a. I want to use hardware PWM, but I'm limited, right? Because I've only got 6 of these hardware PWMs. I want 7. I want to put 7 LEDs on a board, and I want to have them all PWM. And I don't want to just to have them, sort of all shorted together. I want them to be able to independently control them as a dimness factor, right? I want to be able to treat each of these 7 as an analog, right, signal. So how do I do that? This might not be the best way to do it, but this is the way that we came up with. So PWM 0, counter 0, output A, which is OC0A. OC0A is the first PWM output from the first counter. That is on pin 6, which is this 6 over here in the lower right-hand corner. And I will connect that up to the breadboard, and I'm going to basically fan this out to the anode, the positive terminal of all of these LEDs. So I've got it connected here, and so this, remember, this column is shorted, so it connects to here, and it hits this LED, and then I jump it over to this LED, and then I jump it over to this one, and so on. So it ends up shorting one of the terminals of all the LEDs together, so they're shared in that sense. But then on the cathode, which is the other side of the LEDs, I am going to independently connect each of these cathodes to digital pin port D bits 0 through 5 and then 7. So I have to skip 6, obviously, because I'm using that for the PWM output, and I'm going to have them connected. Now you might say, well, why in the world would you do it that way? This is a way that I can time division multiplex the LEDs, because if I set these digital pins to 1, it will reverse bias the corresponding LED and shut it off, right? That way, if I turn them all, if I set the outputs of these pins all to 1, except for, say, this guy, then the PWM output will then control it, because this will be grounded, its cathode will be grounded, and then its anode will be directly connected to this bus, which is the PWM. It's being fanned out to all 7 LEDs. Now you might say, well, yeah, but then that makes it mutually exclusive. Only one can be on at a time. Yes, but if I switch this fast enough, so I can put an analog value, I can set an analog value on my PWM, and just, once I do that, the hardware just automatically does its thing in the background. So I can set my PWM duty cycle, which will control the brightness of the LED, and then I can let it go for a little while, and then I can switch to another LED, and then I can also change the duty cycle on the PWM, and then I can keep doing that. And if I go fast enough, if I do that fast enough, I can trick a human being who's looking at this into thinking that all of these guys are, being independently dimmed and brightened, even though I'm really just doing one of them at a time. You guys with me? Now, so that way I can, now I've got a little demo actually running right now. I don't know if you can see that, but I've got it running. I've got it set up now, and this is basically what I'm going to hope to achieve by the end of the demo here. I've got it running through all 7 LEDs, and they're sort of doing it's sort of doing a shift register. But if you notice that each LED that lights up brightens up, and the one that behind it, dims down, right? Now this is probably not a great test, because it's really just controlling 2 at one time. But I could do the same thing. I could control all 7 separately, but I thought this was a neat, visual effect to have them scrolling like this, have it look like a proton pack or something. Right? Now, Charles was concerned that if you do that, the problem is if you're time division multiplexing in that way, you're also only giving each one of these LEDs attention for 1/7 of the total time, which is, in theory, that would reduce your effective duty cycle to each one individually by a factor of 7, right? Because whenever whenever the LED is reverse biased, it's off. It's going to turn off when you reverse bias it, right? So if I have them turned off if I have every LED turned off for 6/7 of the amount of the total time, it's going to reduce the brightness by a factor of 6/7, right? It would be better if I had some sort of register here that I could use to maintain the value while I service the other LEDs. But we don't have a way to do that yet. There's probably a way to figure that out, but right now I'm just basically turning them off when not in use. However, as you can see, it didn't really come up. It seems to be working fine. These aren't necessarily the brightest they can be. Part of it is because I don't use a resistor. I don't use a shunt resistor like Charles does when he wires these up. He doesn't like to throw the full 5 volts at these things. He likes to feaven it down to like 2.5 volts.
Remember that the reason I do that is because when we ordered the parts for this class, we screwed up and ordered 1.4 volt LEDs. So they blow up if you plug them into 5 volts.
Okay, well these ones aren't blowing up, but it could be because I'm PWMing them. I don't know.
Honestly, that might be why we're still going full brightness. Is because it could be that without without the resistor attached, you may actually be driving it at an effective 1.4 volts. Right?
It could be that, but it could also be that one of the things we used to have a PWM LED lab in my 611 course a few years ago that I used to really like. It was a similar thing, but we did it with the FPGA. And one of the things we noticed with that lab is that if you were to plot the PWM duty cycle versus the brightness of the LED, most people think it's a linear relationship like that, but it actually isn't. In fact, it's more of a thing that looks like this. So if the PWM duty cycle is really low, it's basically off, and if once it gets beyond a certain voltage, it's essentially at full brightness. There's only sort of a limited range that it has near linear behavior, right? So I think Charles might be right. In time division him, I might be effectively bringing down, the point at which I've got it on full brightness. But I'm probably in the saturated region at that point anyway, so it doesn't make any difference. So we haven't formally. I mean, you could find that in the data sheets, I'm sure, for the LEDs, but I think that might be what's happening. But anyway, that's my super long description on. So let's go to my virtual box here. Okay, so I've been, I don't know if this is how you guys are doing. I've just been kind of always starting at the lab UART template. So I now have an empty main function again, which I will delete this crap and start from scratch here. Yes?
Do note that for the next project, there will be a new template, and the main difference is that we're, I think, giving you the header file with the magic numbers for the accelerometer. So make sure that you use that, because re-engineering that header file from scratch will take you a long time, and you'll probably make a typo and then be sad.
It'll be like named lis3dh.h, and so all the register names in the data sheet, like the entire 50-something register map is already shown there as constants. So you can literally just say, oh, use this register name as my address. It's quite nice.
Yeah, so it's like it'll be set up kind of like we've been using with the defines in the 328 header file, right?
Yeah.
Right.
Similar. Includes comments too.
Yep.
So.
Okay, so first of all, let's do some initialization. Okay, so the first thing you want to do is, much like the hardware SPI I did last week, you have to still set up the data direction register for pins, even when you're using them to be controlled by hardware as opposed to GPIO. You guys with me? So I still have to set the DDR-B register, which I'm going to set to FF. I'm going to set all the bits of DDR of the port, not B, sorry, D. So just to show that here. So this is, I don't know how readable that is in the back, but this is the D port, lower right-hand corner. So I'm going to use OC0A, which was kind of a bad decision because I could have used OC1A, which would have put it over here on this header, and then I wouldn't have to deal with this discontinuity with this bit 6. But not a big deal. So I'm going to use bit 6 is going to be my PWM output, and I'm going to use the other 7 bits as GPIO essentially to set the cathode value. So I'm going to still set all 8 bits to 1 in the data direction register. Okay, next thing I want to do is set up the PWM. I'm going to be using counter 0. I have to use counter 0 if I'm using OC0A. So to do this, this part is something that you would only know from digging around in the data sheet. So there's the TCCRA0, and I'm going to set, there's a control bit called COM0A1, 0A1, and that is a bit, COM0A1. That bit is on TCCR0A. So I'm going to set this 1 and that 0, which clears OC0A on compare match. So here's what's confusing about this. OC0A is a pin. It's the name of a pin. But it's also the name of a control register which holds the value you're comparing to. Super confusing. So when they say clear OC0A, they're talking about the pin, not the value, I believe, anyway, right? So we'll set that. So that's COM0A1, correct? Yes. And the other one is TCCRA0. And there's 2 bits in here, WGM01 and WGM00. This is, I was clicking the wrong thing there. That is also in this register. So it's these 2 bits. This is on the opposite end of the register. And we want to set this to be 1, 1. So we want to set OC0A on compare match, clear it at bottom. What does that mean? It means that what we're expecting to happen is we have a counter, an 8-bit counter. Counter 0 is 8-bit, so it's going to count from 0 to 255. We're going to put the duty cycle into this OCA0 register. We want it from 0, from the time the counter rolls, the odometer on the counter rolls back to 0. We want to set the PWM output high. Once it hits that value that we're comparing, we want it to drop it. Then we want it to remain low until it rolls over again, right? So in other words, we're going to count from 0 to 255. That's going to be our period. And you can have it count however fast you want. Like you can set no divider on the counter, or you can set a divider which will slow the period down. But we're going to have this period, and then from 0 to whatever you specify. So if I put 127, for instance, that would be a 50% duty cycle because it's going to count from 0 to 255. It's going to be high from 0 to 127 and low from 128 to 255, right? And so that's what this this WGM thing, the COM rather. This is the, actually wait a second, let me go back to that. Now I've tripped myself up. WGM0100 and COM0. COM0, so it's COM0, so we're going to set COM-A0, this guy, so this will put it into this mode, toggle on compare match, and then for these guys we're going to set it to 1-1, which is inverting mode. That's what gives you this 1-0 as opposed to 0-1, right? And when I say 1-0, I mean 1 from 0 to whatever the compare value is, and 0 from the value after that to 255. Yes?
Is the OC, the thing that's the 1-1, is that the same, is that the pin, or is that the data register that's...
I think that's the pin. Because, I don't know if you remember, but last time I mentioned that when I was using the interrupts, so when I was doing the hardware SPI, I also used this OC0A to trigger an interrupt. You can set the interrupt when it rolls over, or you can have it trigger an interrupt when it hits that value. But when I was using it to generate the interrupt, I wanted the counter to reset that value, or reset the counter. Or I couldn't get it to reset the counter, so I had to do it myself in the interrupt service routine. It's the same thing here. It just changes the pin. It does not change the compare value or the counter value itself. The counter just keeps rolling, and just keeps rolling from 0 to its max value and rolling over, right? I never did figure out how to make it clear the counter in certain cases. I just did it in software. Okay, so I think that's all we have to do, right? Let's check my notes here. Oh yes, and then that's the only thing we have to do in the A register. Then there's TCCR B0, And there is a bit in there called CS00. And that is in the B register, which is this guy. And it's CS00. Now, if you look at this, you say, wait a minute, there is no CS00. The CS10, so CS11, CS10. Well, remember that 1 is referring to counter 1 because I grabbed the screenshot from counter 1. So CS00 or CS10 for counter 1 is basically just saying no pre-scaling, which means this pulse width modulator is going to have a period of 256 over 16 million, right? Because the clock, if you don't do pre-scaling, this counter is going to tick up one time every 16 millionth of a second. And so the period in seconds is going to be 256 over 16 million. That's pretty fast, as fast as we can run it on this chip. Okay, all right, so I got that set up. And then the last thing to do is to just pretty much just set your duty cycle. So OC0A, 0A. If I set this to 127, for instance, this will give me my 50% duty cycle. Sorry, it's OCRA. OCR0A. That's right. So maybe it isn't the same as the pin, is it? The pin is called OC0A. So the R, okay, sorry, I was mistaken about that. So the name of the register that controls the duty cycle has an R in it, OCR0A. So it's slightly different from the name of the pin. Still close enough that it confuses me. All right, so now what? What do we want to do? We can just have all the LEDs go together, right, if we want to, just to start out, as opposed, so we can do it in a mode where they're all tied together as opposed to time division multiplexing them. Let's see. I want to make sure I follow my example this time so I don't get in trouble like I did last time. So if I want to have them, let's say I want to have them do that breathing thing that Apple did on their on the MacBooks like 10 or 15 years ago, where it kind of gets brighter and then it gets dimmer and then it gets brighter and dimmer, right? I always thought that was a neat effect. So in order to work that out, we need to have a state. We need to have, the program is going to have to know which way it's going. Are you going up or are you going down? Are you getting brighter or are you getting dimmer? So I just had a variable, a uint8 called up down, which I initialized as 0. And then this whole thing will be inside of an endless while loop. And I'll say if up down equals 0. So if it's 0, I'll tick it up by 1. So I'll say OCR 0A plus plus. So increment. Now keep in mind that in order for this to work, this register has to be readable as well as writable. And if you look at the data sheet, it turns out it is. You can't always assume that you can read a register like this, but you might say, why do you have to read it? Well, you have to increment it. So in order to increment, you have to read it, add 1, and then store the result back. So, but that does work. Initially, I was afraid to do that, so I had a separate variable that kept track of that instead of just using the register directly. And then else OCR 0, 1, minus, minus. And then if up down equals 0, and so if I'm going up and I max it out at 255, so OCR A equals A0A equals 255, then I'm going to go down. If up down equals 1, and OCR A 0A equals 0, then up down equals 0. So if I'm going up and I max it out, I'm going to tell it to go down. And if I'm going down and I zero it out, I'm going to tell it to switch to go back up. Okay. Now the problem is that we have two different time scales now, right? Because you've got, this is the thing that makes this a little difficult, because you have the PWM time scale, which is operating at 256 over 16 million, but now we have another time scale that we're using to control the brightness, which is a separate time scale, and that needs to be much, much slower, right? Because otherwise, it's going to go so fast, bright, dim, bright, dim, bright, dim, that it's just going to look like it's kind of in the middle, right, when you look at it, right? So how do we slow it down? Well, the easiest way to do it is to use a, just put a delay in. Now, how much do I delay this? Well, what this is going to do is to go up from 0 all the way to max is going to be 256 milliseconds, right? It's about a quarter of a second. So it's going to take a quarter of a second to go up and a quarter of a second to go down. So in a half a second, it's going to be the period of that thing. Probably too fast, right? Maybe it should be slower. I'll make it 2. Okay, and then finally, the other thing I'm forgetting here is, remember the cathode of these LEDs is connected to the GPIO pins, right? The port D. So here's where I'm going to get. I'm going to show you a couple little tricks here that you can use for this stuff. So now there's a couple issues here. One, I want to be able to set pins to be 0 or 1. And in the past, I've kind of just done it in an ad hoc way in the code, but I want to do a little better job of that this time. So I'm going to define a macro called setBit. Are you guys familiar with macros, pound defines? Probably. So you might have used them as constants before, like in 240. You can also use them, you can also send a parameter into a macro. So I created this macro called setBit, and I have a parameter called port that'll be like port A, port B, port C. Or no, sorry, there's no A. B, C, or D. Port B, port C, port D. And the pin that I want to set and the value I want to set on it. And then I can put this little if statement and say if val, right? If val is 0 or if val is 1, then I can do port, and I can use the convention we use to set a bit to 1, which is I can take the port and I can OR it with 1 shifted by the pin. Make sense? Right? Else, I can do the other convention, which is port ANDed with the not of 1 shifted by the pin. Does that make sense? If val, set the pin to 1, otherwise set it to 0, right? Yes?
So essentially, you're going to use this to turn on and off the different LEDs, the 7 different LEDs. You're just going to pass through the different ends and
Exactly.
what they're set up on.
Yeah. But you could use this for any GPIO for whenever you're doing a single bit access. If multi-bit stuff is not going to be as convenient, but so this macro allows you to set a single bit on a single port. Okay. Okay. Now the other problem is question?
Yeah.
Yes.
Why don't you just? I knew you could do this, but what's saving you time instead of doing a function? Why are you doing this?
That's a good question.
Let's type it.
Yeah.
I see you don't have to set the type of what you're passing in there.
The function probably would be equivalent, because normally people would say functions have an overhead. Like whenever you call a function, it has to push a record on the activation stack, which implies that you have to save the return address and save the state of the registers and take some time. But compilers are smart enough to realize that if the function is small enough, it'll just inline it. So basically, this macro is doing an inlining. It's inlining that command, so it's because it's the preprocessor is actually going to insert this code everywhere I reference that set bit before it even gets to the compiler. But I could have done a function, would have been just as good.
It
Right.
might be, well, so for one thing, it might be worth noting that this is kind of almost equivalent. GCC specifically has a flag that's, you can say like it's like double underscore always inline before a function. which would basically make it the same as this, other than it would have type checking.
Or you can just say inline.
Well, inline GCC
Right.
doesn't honor, and it doesn't feel
Yeah.
like it. It pretty much just ignores it and then makes its own decision. So
There's a special attribute flag you can put on it.
Yeah.
Under GCC that forces it to inline.
Yeah.
Whether it's a good idea or
the
not.
other thing
Yeah.
to note, especially in the context of being an embedded systems class where you may have to work with weird vendor-specific compilers, is that different C compilers handle this differently. So I worked on a large C code base at one point in an open source project where the maintainer actually had a feature macro flag that could flip all of the main functions from being defined as functions, inline functions, or macros, depending on which one worked best with which compiler he wanted to use. So this is kind of, in theory, this should just be the same as doing an inline function but without type checking, but some compilers may like this better and some compilers may like inline functions better, and you should probably read your compiler's manual and have opinions on it if you're actually doing this for real.
Yeah, I didn't put any thought into this at all. I thought it was a short little simple thing, so I just did it as a macro.
Basically, we're
I don't
doing
even-
we're doing the inline at the source code level.
Yeah.
If that makes sense.
No, that makes sense.
Yeah.
Okay, now the other thing I want to, another trick I want to employ here is I want to create a mapping. So I'm going to have 7 pins. I want them to be enumerated 0 to 6 rather. But those 0 to 6 map onto the port D pins 0 to 5 and then 7, right? So I'll create this a little map array to handle that as well. So UN8 type LED map, which will be 7, and I will initialize it as DDD0, DDD1, DDD2, DDD3, DDD4, DDD5, and then DDD7. I'm going to skip 6. Okay, so this way I can translate between my LED pins and the actual pins, right? Yes?
What is DDD?
DDD is, if you go over to, the header file, the IOM 328p, for the DDR, it's actually part of the DDR. Yeah, I could have just used numbers there. It would have been easier. But this actually, it comes from the header file.
So it's the same thing as using head.
Yeah, they're macros. It's the same thing as putting 0 to 5 and then 7. Okay. Let's see. All right. So I can write a little for loop here at the beginning to initialize those guys. So for uint 8 type I equals 0, I less than 7, I plus plus, I can do set bit port D is my port. The pin is going to be LED map of I, and I want to set them to 0 because we're using negative logic here. You know, setting them to 0 is going to activate that LED because it will ground the cathode. Right. The other thing, though, I was thinking about this. It's like, you know, you're setting it to 0, but all of the current that passes through the LED is going to come back into that GPIO. It's going to be sunk, but it's okay. I mean, it's because you're pulling that down to 0. You're just sinking it through the pull down resistor. I don't know if that's good for the chip, but
As long as you're sinking less than 80 milliamps, it's fine.
okay.
It's in the manual. Anything over 80 is where it starts to get upset. But I think it can source less than it can sink. So
Yeah, which is meaning that if I had something on here that was a higher power device than an LED, I may fry my my 328 by doing this, but it'll be okay in this case.
just use a MOSFET. It's really easy.
Or I could have used a MOSFET, but I wanted to simplify my breadboard design. But all right, so okay, so is that it? I guess that's it, right? I'm sure I screwed something up, but I've got my PWM initialized here. Pretty easy. It's just 3 lines of code to set that up. Well, 4 if you include the initial duty cycle there. So I'm going to start out at 127, but I'm going to also start out going up. So it'll start at 127, it'll go up to 255, and it should come down and up and down and up. It should do that at a period of roughly half a second if I did the math right here. There's my state. That's my initialization. There's my infinite while loop. We should be good to go. So I'll save that and then make burn. Oh, wait a second. I'm sure. Hold on. Before I do that, change mod 777 dev bus USB 001. Which number is it? 12? Okay. All right. Now that should be able to burn that. Okay. Yep. I screwed that up somehow. Okay, so it burned, but my LEDs are dead. So let me check. Yes?
Are you actually putting like the value of the lights? Like you set them to 0, but like how, like where's the, turn it on?
So the value is the OCR 0A. So all of these are all connected to the same PWM output, which is connected to the OCR 0A.
Okay.
So this controls the brightness. So this value is going to be between 0 and 0 would be 0, and then at some point it'll start to turn on, and then it'll get brighter in the linear region.
Okay.
So anything between 0 and 255 should you should start to appear on once you get past 50 or so, right?
So do you not have to call that to the actual LEDs themselves, like in the sense of like passing it, like using the macro that you defined at the top there, like?
No, I only use the macro to set to activate the LEDs as being on or off.
Oh, okay. So
Right.
all it really does is just an initialization of like these lights are on.
Right.
Or, like I'm going to use these lights.
These lights will be connected to the PWM source, essentially. The other ones will be off. So by setting all these guys to 0, so I set the DDRD to, so the data direction is all 1s, right? And then I had a thing here where I set each one of these guys to, I actually didn't need the semicolon there because I think I have the semicolon up here in the define, so that was redundant, but it's all right. But so this will set all of the outputs there to 0, right? So it'll ground.
The lights,
What's that?
that would turn them off, right?
That would allow the lights. This is, yeah, it turns off the cathode, so it's going to allow them all to be controlled by the PWM. The PWM value itself is controlled by OCR 0A, right?
You don't have to pass that PWM value into the LEDs, like with using the set bit function?
No, because that's the value. That's the beauty of using the hardware PWM. Now, if you were doing software PWM, which you're actually going to do in Lab 2, then you do have to do that, right? So that's an important distinction there. Is that in this case, I'm setting that PWM strictly just by setting OCR 0, whereas because I'm using hardware. If I was using software PWM, which I could do instead, you would have to set it on or off explicitly with code.
If you're using software PWM, would that be like, instead of using that OCR 0A, would that just be a variable that we count like up and down and then pass
Right.
that in through the function?
Yep,
I assume?
exactly. Yeah, or you could just use a weight.
Okay.
There's a delay. Like you could say, well, I want a 50% duty cycle, so I'll put a delay, 50 microseconds, turn on, delay 50 microseconds, turn off. And then if I want a 25% duty cycle, my delay for having it on will be 25% of whatever the total time is.
Okay.
Right? So you could use the delay. There's a microsecond delay, right? Yeah.
The timer.
It's US.
US.
Do delay underscore US.
Yeah, I'm using MS here because I don't have to worry about microsecond time scale because the hardware is taking care of that for me.
Okay.
Okay, so TCCRA is COM0A1, WGM01, WGM0000 here. Set this guy to 127. set all my bits. Just in case this is the issue, I'm going to also set port D. Port D, I can set this to be 0. Actually, I just set the whole thing to 0. And let's see. So if my up down is 0, so we're going to start up down at 0, which means up, which is kind of counterintuitive, but I'll increment that. OCR 0, 0, 0A plus plus, 0, OCR 0A minus minus. If I get to the top. Okay, now if you run into an issue like this, there's some sanity checks you can do. For instance, I can set this guy to be 255, which should turn him on. And then I can just pretty much just stop it there. Okay, so I think maybe one of my wires got disconnected here. So you can see that this should, now another option would be I can, instead of using the PWM, whoops, you can comment this stuff out, and I can just set the pin directly. So remember port D6, I'll just comment that out, and I'll set port D equals port 1, 6, so I can set bit 6 on, and I can set the other bits off. Port D actually, you know what, let's do it this way, be easier. I'll set everything to 0, and then I'll set everything to 0, and then I'll set just bit 6 to 1. So that will override the hardware PWM and should light them all up. And that's not working. Yeah, so I must have a disconnect here. I probably pulled one of these guys out somewhere. Bit 6. Yeah, I don't know. I'm not getting them turning on. All right. Well, it's not a big deal. We can, if I do have a bug, I'll figure it out and send out the updates. I send a fix out. I don't see any issues though. Charles, you see anything here? DDR0. It's really not doing anything but setting everything to.
Is it throwing an error?
No, it's just not lighting them up. I think I might. Maybe I have it. It's one of the issues is I've got.
Well, you may want to do.
Oh yeah, there we go. Actually, I think I found it.
Well, I think so. If you're doing one. Did you pick Did you pick? Wait, isn't?
What's that?
Did you pico?
Did I what?
Did you pico? I didn't see you.
No, I'm not using PicoCom. I just skipped that part.
Wait, why is there a...
Do you want that to be a one shift 5? Because I thought you were using PD6 as your PWM output.
Yeah,
Why is the...
I'm overwriting it.
Does that work?
Yeah, so we commented out the PWM setup code here, and I'm just setting that to 1 and the other guys to 0.
Yeah, that should. Yeah, I'd expect that to work then.
Yeah.
Did you remember to set? Okay, and you set DDRD to OXFF.
What's that, Philip?
Why is there a while 1 there again?
Oh, I'm just making it stop there instead of going. I want to rule out any bugs that are down here.
Okay.
Yeah.
Okay.
Yeah. So every time I run into an issue like that, you want to rule out possible sources for bugs and this is just a sanity check, right? So if everything is wired up correctly, if the bug is here, it's not going to get there. It should have just set the the brightness value to 255 and it should be lit up. That didn't work. So I said, well, it might be a problem with the PWM. So you get rid of the PWM and now it's just hardwired to just light everything up. If it doesn't work then, it's got to be a connection problem.
You could rule out a wiring problem by just connecting a single LED directly from
Oh,
PD5 to PD6.
Yeah, that's a good one. So if I take PD6 out and I just go VDD on here, yeah, so even that's not working.
Yeah, so your ones that are syncs ought to be synced.
Oh, there we go. I got one.
Sources ought to be sourcing.
Yeah, yep.
So that's a good way to test.
So I got one, yeah. So I took the 5 volt on the board and I plugged it into what I normally had in the PWM output, which is bit 6 of port D. And when I did that, I'm just getting one LED lighting up here. So there is a connection issue here. I was worried that this might get.
LEDs backwards?
Well, no, I had it. Yeah, I had it working earlier when I brought it down.
Well, what happens if you flip if you make port D be all high and then do just set PD6 to 0?
No, I could try that.
And that's an easy thing to check, right?
Yeah.
I mean, that's any time that there's 2 possible ways that something could be, I just always check both to be sure because it's usually easy to check and sometimes it works.
No, that wasn't it. Yeah, I didn't. Yeah. Okay, well that's not a big deal. I'm going to move on to the next part here. So how would we, I'm going to just assume this is okay for now because I had this working fine earlier before I came down. Okay, so I'm going to reset this to 127 and okay. All right, so let's see how much time do I have? About 15 minutes. Okay, so now how would I individually control the LEDs as opposed to having them all do that breathing thing, all being shorted together? This part is a little bit more challenging because there's 2 problems you have to solve. The first is you want to be able to control the state of all the LEDs separately, right? So for that, I just created an array, uint8_t, called LED vals, that is 7, and initialize them as having the first one fully on, and then the other 6, yes, the other 6 turned off. So the idea is that the PWM value for each of the LEDs will be stored in this array. And so that way, when I context switch and switch to another LED to do the multiplexing, to do the sharing, I can retrieve the value of that corresponding LED in here because I can't just rely directly on the PWM intensity register itself because that's only going to hold the value for one, right? Okay, and then inside my while loop, we will also, now this part took me a while to figure out. So I want to be able to control, I want to have one LED that I'm charging up essentially, and one LED that I'm bringing down, right? Discharging, right? So I tried a couple different ways to do that, but the logic became a little tricky. So to simplify it, I just created another variable called LED active, which I set to 0. And so, oh, sorry, and actually, we can initialize these to 0. So inside the while loop, so I can get rid of, actually I'll just create a new while loop. I'll leave this one here so we can switch between the two if we want to go back to the having them all breathe. So, so we're going to go through a refresh cycle where I'm going to go through each of the LEDs and update their counts, right? So for uint8_t, I'll call it I equals 0, I less than 7, I plus plus. Let's say if I equals LED active, then I want to increment that LED val. Okay, otherwise, if LED active of I is greater than 0, then I will decrement it. So LED active specifies the LED that's brightening. So there's only going to be one of those brightening at a time. And presumably, if I do this right, there's going to be one that's going to be being dimmed, right? So anything that's not active, but it still has a, sorry, vals. I got that wrong. Vals. If LED vals, if it's got any charge left in or any brightness in LED vals, then I will bring it down. I will. So this is brightening the LED, and that's dimming the LED, right? Does it make sense?
You need to ask what your brightening of vowels.
Oh, sorry, vowels. Yes, vowels. All right. Okay, so that'll update the state, and that's going to happen once per iteration of this loop. Okay, now I need to go through and I need to activate each one of the LEDs separately, right, in order to create this effect, this sharing effect. So I will go through all the LEDs again. So Ti equals 0. And actually, I'm going to make this, I'm going to do this separately, actually. So in a separate loop, after you update the values, we'll have a un8 underscore t, I equals 0, I less than 7, I plus plus. And we will set the LED, the OCR 0A to be LED vals of I. Make sense? So this will set the brightness of the one PWM output, and then we will activate whichever one of those, whichever one of the LEDs we want to be turning on at this time, right? So to do that, I will do another for loop here. uint8 underscore t, j equals 0, j less than 7, j less than 7, j plus plus, and we will say if I equals j. So in other words, we want to activate number I, right? So if that's the one we're activating, then we just have to set bit on that guy. So port D, bit J, and we want to turn it on. Remember, on is 0, right? Well, it's not on, but it's connected to the PWM, right? Otherwise, we will set bit port D, J, and 1, which will disconnect it from the PWM. Okay, so, and then we have to give it some time. You know, we have to give this a little bit of time because we want to have each LED, we want to go through a number of PWM cycles for each LED before we move on to the next. So we can put a delay in here. Delay, put microseconds 100. Let's see, how much did I delay it here? Now we could just do 1 maybe. So this will go through all 7 LEDs and give them all some time with the PWM. Make sense? All right? Sorry? Yes. Oh, yes.
So, if you set the bit to port D of J to 1, is that pin like floating instead of a sync?
No, if you set it to 1, it does it reverse biases the diode. So it brings up one of the sides that's supposed to be the cathode, which is the second side of the LED, it brings that up to 1. And that's not going to allow, that's going to reverse bias it. It's basically, it's going to make the other side, it's going to try to send current the opposite side through the LED,
Okay.
which it's not going to allow, which turns it off. Right. But by setting it 0, then it puts it grounds one side of the LED and the other side is connected to the PWM.
Yeah.
So that'll allow it to control the brightness. Yep.
So these pins they can be either in or out, or just exclusively out, but you set it out.
Well, it's an output pin, but you're right. It's actually sinking current, though. That's what I was talking to Charles about earlier, is that you're setting it to 0, so you're grounding it, but what you're really allowing it to do is it's an output that you're pulling down to 0, but there's current going to be coming into that pin,
Yeah.
and it's going to be sinking current. So it's weird. Logically, it's an output, but electrically, it's an input. It's sinking current inside of it.
As I recall, right, the actual what their standard library calls input mode is actually floating because you're allowing something else on the bus to pull the bus up or down. So.
Any questions about that? Okay, now the only thing I've left out here is I don't have the ability yet to change the LED active. So how am I going to do that? So basically, once I increment it here, I need to check to see if I've maxed it out. So if LED vals of I equals 255, then I'm going to set LED active LED active to be equal to, if LED active equals 6, then I want to reset it back to 0. Otherwise, I'll set it to LED active plus 1. So you see how that the LED active is going to go from 0 to 6 and then back to 0 again. So I use this little trinary operator where you check to see if it's already 6. If I've already at 6, then I'll roll it over to 0. Otherwise, I'll just increment it. Make sense? So this is what will make the LED move. This will start charging up 0, then it'll charge up 1, 2, 3, 4, 5, 6, and then back to 0. Now, meanwhile, whatever the LED that was active previous to that will be discharging, because every time I run through this loop, I will discharge, or I will dim out the one that's not active. Right, as long as it's still got some brightness in it. Yes.
So you have to hit 0 to 255 in a full cycle.
Yeah. So when it brings it up, it's going to bring it all the way up to 255. So I have 2 time scales in this loop. There's this loop that's going to go through all the LEDs, and every time I switch LEDs, I'm going to reconfigure the LEDs, right? Which one's connected to the PWM? That's why there's a nested loop here. So for every LED, I want to give it some time. So to give it some time, I'll reconfigure I'll reconfigure which one's got the floor, right? Got the access to the PWM, and then I'll put a delay in there, right? Oh, and I don't want to do I don't know if I want to do 1 microsecond. Probably longer than that. Maybe 1 millisecond, actually. Yeah. Okay. So this loop nest here will take care of the time division multiplexing, and this loop up here will just control the relative brightness of all 7 LEDs independently, separately, right? As 7 separate analog values. Make sense? And that would produce the effect I had when I first came in, when I still had my connections working. Any questions about this?